Hey guys, welcome to another lecture from Introductory Statistics. What are we working on today? Today is a special one. We have worked on around 30 lectures in statistics and probability. And today I want you guys to revise probability with me. I'm going to divide these 30 lectures in two parts, probability distribution and probability. I'm going to revise probability with you guys today. And in the next part, we'll revise probability distribution, the discrete random variables that we have worked on. So when you start working on probability questions, there are certain things that you should be very clear about. Within an experiment, what gets created is a sample space wherein you denote all possible outcomes. Sample space is a set of all possible outcomes, and out of which there are certain events that can happen. So, events are basically collection of certain outcomes. It could be just one outcome, and that's simple event, and it could be compound event, that is it consists of more than one outcome. These outcomes are the outcomes from the sample space. So of course events are subset of the sample space. With that, we started our probability and we started creating sample space for certain experiments. For example, out here, consider an experiment in which each of three vehicles taking particular freeway exit turns left or right at the end of the exit ramp. So how many possibilities are there? Since there are three vehicles, it could be right, left, and so on and so forth. So all possible combination of left, right in three positions you have to mention. So of course there will be 8 such outcomes, and 8 is the number of outcomes that you will have in your sample space. Okay. And within the sample space, then you can create different events. For example, even that all three cars are turning right. So that would be right. Similarly, there could be different kind of events that you can create. Sometimes your sample space is finite, but sometimes your sample space might be infinite. For example, we took here flip a coin until first head occurs. Now, in this situation, the sample space will be starting with head. That is the possibility that in the first, on my first roll, I get head. Then it could be the case that I get heads in the second time, then third, then fourth, and so on and so forth. You don't know where to stop. Maybe it keeps on going on and on and on. Okay. So therefore, sometimes it can so happen that your sample space consists of infinitely many entries. Similarly with events. Okay. What if I want to find the event where head occurs or at an even position? Now, even position starts with the second position, then fourth, then sixth, but you don't know where to stop. So sometimes sample space and events could be, these sets could be infinite in nature. And within probability, since the language that probability uses is the language of sets, therefore I revised entire set theory with you guys. Even sample space, all that we're talking about are sets. So we spoke about what are complements, what are the operations complement of an event A, which we denote as A dash, is a set of all outcomes in S, the sample space, that are not in A. It's a very important concept when it comes to probability, the concept of complement events. Union, intersection, extremely important, and we discussed thoroughly the union of two events A and B. A union B consists of everything that is in A or in B. Okay, that's either in A or in B. So if you take any event A and its complement and unite them, you will get the entire sample space. Similarly, intersection. If you take any two events A and B, intersection would consist of everything that is in A and in B. Everything that is in A and in B. So therefore, in case I take the intersection of A and A complement, I will get something which is called phi, the null set, which consists of nothing, right? Then a very important concept in probability, the concept of mutually exclusive events. Mutually exclusive or mutually disjoint basically means that you take two events A and B. They would be mutually exclusive. That means they don't have anything in common. So their intersection has to be phi. Like A and A complement, they are mutually exclusive. So whenever there is, nothing in common, it's mutually exclusive. Similarly, the concept of A minus B also is very important pictorially. Basically, if I look into A minus B, it means only A. So it consists of all the elements in A that are not in B. So A minus B and B minus A are two very different things. Always be very careful with that. Then comes De Morgan's law. Again, even in probability, it's important. You should know the relationship between union, intersection, and complements. So De Morgan's law basically tells you that if you take A union B complement, it is nothing but A complement intersection B complement. If you take A intersection B complement, it's nothing but A complement union B complement. And you can extend it to n events. So union AI, for example, is basically A1 union A2 till AN if I'm taking the union till N. So if you take this union of n events and take its complement, it will be equal to A1 complement intersection A2 complement, so on and so forth till AN complement. Okay. Which you can write down as the intersection of the complements like this. Similarly for the other part. And with the basic knowledge of set theory, we are able to calculate probability. Probability in terms of equally likely outcomes, probability in terms of when it's not equally likely outcomes. So here, if we take equally likely outcomes, first of all, what do you mean by equally likely outcomes? So in many experiments, what happens that you consist of capital N say outcomes. So sometimes it's reasonable to assign equal probabilities to all n simple events. For example, tossing a fair dice. So when you toss a fair dice, so you have six numbers, 1, 2, 3, 4, 5, 6. So it's fair enough, to give it 1 by 6 probability to each number. The possibility that I will achieve 1 by tossing is 1 by 6, 2 is 1 by 6, so on and so forth. Selecting one a card out of the deck of 52, equally likely, equal probability to each card. Selecting one ball out of 10, equally likely. So sometimes what you can do is you can just give it one single value to the probability equal in case there are n total outcomes. So the equally likely probability will be 1 by n. Okay, herein I gave you an example. You have 600 mysteries on your bookshelf and 600 science fiction. The first three of each type are hardcover and the last three are paperback. Consider randomly selecting one of the six mysteries and then randomly selecting one of the six science fiction to take on a vacation. What is the probability that both selected books are paperbacks? So here in this question, there were two things, hardcover and paperbacks and six mysteries, six signs. Within mysteries, you have three, half of them are hardcover, half of them are paperbacks. Now, what are we saying? We want the probability that both selected books are paperbacks. It could be whether science or mysteries, but paperbacks. So 1, 2, 3, 4, 5, 6 mysteries are there. Say 1, 2, 3, 4, 5, 6 signs are there. So the combination of mysteries and signs, what you can have here is like just two dice basically, 1 to 6. So 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, so on and so forth. Similarly, 3, 1, 3, 2, 3, 3. Now, you can have 36 total outcomes because there are 6 mysteries and 6 signs. So total outcome 36, out of which what are your possible cases? What are the possible cases? See, paperbacks. We want only paperbacks, whether it is maths or whether it is mysteries or science, but paperback. So we are saying that the last three are paperbacks. So if last three are paperbacks, that means paperbacks would be three, whether it is mysteries or science. It would be, it should consist of four or five or six, four or five or six. Okay, so how many possibilities are there? There are three possibilities for mysteries and there are three possibilities for science. So therefore, nine total possibilities are there. So 9 out of 36. 9 out of 36 will be the required probability. Now, this required probability, there's another way to look into it. That's what I tried to teach you in this lecture. That each book is equally likely to be picked. So 1 by 36 is the chance for each book. Okay. And now, how many outcomes are favorable to us? How many outcomes are favorable to us? If you create these 36 outcomes, you will figure out that the outcomes that are favorable to us are 4, 4, 4, 5, 4, 6, similarly 5, 4, 5, 5, assuming that 4, 5, 6 is the number to the given to the paperbacks. Okay, so similarly, with 6, so you will have 9 such outcomes. So when A is the number, if you take A as a number of outcomes, in case you have more than one outcomes in the equally likely scenario, probability of event A is number of outcomes in A. That is the total of all those outcomes. As I said, 1 by 36 is the equally likely probability, but there are 9 such cases that have to be included. So that is why 9 by 36. So when we started calculating probability, we realized that counting techniques were extremely important when it comes to calculating probability in questions. So therefore, we started working on the counting techniques. As we did in this previous example, we realized that probability of A is basically the number of outcomes in A upon the total number of outcomes because of equally likely scenario. Okay, so that's why I'm not saying favorable outcomes upon total outcomes. I'm saying number of outcomes in A because it's equally likely scenario upon capital N. Capital N represents the total number of outcomes. Okay, so we realized how important counting techniques are. Suppose you are doing some remodeling which requires the services of both plumbing and electrical contractors. In how many ways can the contractors be chosen if there are 12 plumbing and 9 electrical contractors available in the area? So, how many such choices will I have? I have 12 plumbers and I have 9 electrical contractors. I have to get both the jobs done. So, for plumbing, I have say P1, P2 till P12. For electrical, I have E1, E2 till E9. So, this is where you use the concept of ordered pairs, you use the concept of multiplication rule in counting. Since I have 12 options for plumbing available and 9 options for electrical work. So say if you opt for plumber number 1, P1, and then make a choice for the electrical work, E1, E2 till E9. So you have 9 choices from here. Then similarly could be the case of 9 choices with P2 fixed and so on and so forth. So you'll have 12 such cases. Therefore, you have 12 into 9 total possibilities, and that's what is the product rule in counting. Suppose you have moved to a new locality and you are searching for easily accessible dentist and general physician. In the 5-kilometer radius, suppose there are 4 physicians and 6 dentists available. How many options do you have in total? I need a physician and dentist, and I have been given that within 5 kilometers I have 4 physicians, 6 dentists. So in total I have 24 combinations, 4 into 6, that could be that are possible for me. Okay, out of which I can create any one combination. Now suppose further you want a physician and dentist at the same medical center. Suppose now you want these two doctors at the same medical center, and you know that there are two centers around each, having two physicians and three dentists. In how many ways you can choose a physician and a dentist from the same center? Now it's a different question. You want them to be sitting at the same center. You don't want to go to two different places. Okay, you know that there are two centers, each having two physicians and three dentists. So how many choices do I have? So suppose in that case, if we say that medical center 1 has P1, P2 physician and D1, D2, D3 dentist. Similarly, medical center 2 has P3, P4 physicians and D4, D5, D6 dentists. So therefore, how many cases do I have? So if I want medical center 1, I have one choices of medical center 1. From the medical center 1, how many choices do I get? I get the choices of two physicians and the choices of three dentists. So I get 6 choices from here. And medical center 2, I get 2 into 3 again. That is 6 choices here. So that means in total, I have 12 choices, whether you look at it from the point of view of 4 times 3, or basically 6 plus 6 cases, or you look at the branches. I've shown you how to go through this in any way that you wish to, but this is what you will have to do in this particular question. So the product rule for k tuples, not just two tuples, the ordered pairs, but for k tuples, suppose a set consists of ordered collections of k elements and there are n1, n2 till nk possible choices for the first, second, and so on and so forth, kth element respectively. Then there are n1, n2 multiplied by n3, so on and so forth, till nk possible k tuples, the way it was happening here. For example, now in case, suppose the home remodeling question that we did, it also involves first purchasing several kitchen appliances. They will all be purchased from the same dealer and there are 5 dealers in the area. So now if I'm also including kitchen work, with the dealers D1 till D5, there are how many ways to choose a dealer, a plumber, and electrician. So this time you have 5 dealers for the kitchen, you have 12 plumbers, and you have 9 electricians. So in total, these many options I will. With this came in the most important part. In case of calculating probabilities, it's extremely important to be comfortable with permutation combinations, and that's what I tried working with you guys on through certain examples. So consider a group of n distinct individuals or objects. How many ways are there to select a subset of size k from the group? Now these kind of scenarios call for counting. Example, suppose you have 15 players, baseball players, and you have to select a 9 from a starting to form a starting lineup. Suppose you have a shop that has 10 laptops and only space for 3. So in how many ways can I choose these 3 laptops to display? There are 2 cases in these kind of scenarios. One case is where the order matters and another case is where order does not matter. In the baseball case, okay, now in the baseball case, because you have pitchers and catchers in this game of baseball, so suppose A and B are 2 people who are getting selected in the lineup. A is a pitcher, B is a catcher, is a different case compared to B is a pitcher and A is a catcher. So in these kind of scenarios, order will matter. But there could be certain scenario where order does not matter. In the laptop case, if you want to put any three for display out of the 10 laptops, do you think the order will matter? No, the order perhaps will not matter if they're almost like the same kind of laptops. Okay. So because sometimes in this case, perhaps in laptop, somebody who's just watching it would needs to look into the shop and needs to see, okay, laptops are available here, right? So it doesn't matter which laptop is out there. When order matters, then the counting arrangement is called permutation. When order does not matter, then that counting arrangement is basically just selection and it is called combination. Then we learned that just the name, then we learned that what is behind the names, okay? What exactly is permutation? What exactly is combination? Permutation is NPK, combination is NCK. NPK is n factorial upon n minus k factorial, and NCK is n factorial upon k factorial into n minus k factorial. Now, how and why this is happening, we did it through certain examples. Suppose a college of commerce has 7 departments, which we denote by A, B, C, D, E, F, G. Each department has one representative on the college student council. From these 7 representatives, one is to be chosen as a president, another as a vice president, and third as general secretary. How many ways are there to select these 3 officers? So you need a president, vice president, and secretary. Okay, what options are available to us? So there are A, B, C, D, E, F, G. These are 7 departments, and one person from each department is there in the representative council, okay, as a representative in the council. Now, out of these 7 representatives, one, 3 of them would be selected as president, vice president, and secretary. Now, does the order matter here? Yes, the order matters because these are people. If somebody is a president, is a different case compared to somebody, that person being the vice president. So therefore, the order will matter here. So here in the first position, say for the president, I have 7 options. Now one person selected is the president, goes out. So for vice president, I only have 6 options available. And for the general secretary, I have only 5 options available. Okay, this is the case where order will make a difference, because say I am Vidhi, I am the president. In one of the cases, I am the president. Nishant is the vice president and Aditya is the secretary. And the case where Nishant is the president and I am the vice president and Aditya is a secretary, these two are 2 different cases, and so on and so forth. That is what you mean by order matters. So always remember, when you're arranging, then order matters. When you're selecting, there are 7 people, I want to select 3 people. Just selecting 3 people, not giving them any position, just selecting 3 people, that's combination. That's purely just selection. Like for example, in the same example, say, suppose 3 out of the 7 representatives are to be selected to attend a statewide convention. So it's not about positioning, okay? You just have to select. Order will not matter here. If I just need to select 3 out of these 7 people, 7C3 cases would be there, and which turns out to be much lesser in number. Always remember, it would be much lesser in number. In fact, because the ordering doesn't matter. So if Vidhi, Nishant and Aditya are selected, they are selected. It doesn't matter in which order I'm writing it. Okay. That is why you will see that when it comes to combination, the formula also gets divided, because you, in some sense, depermute. So it's 3 factorial 7 minus 3 factorial. After understanding the calculations behind simple probability questions, we worked on the concept of conditional probability. Extremely important because with conditional probability comes in a lot of concepts. The concept of Bayes theorem, multiplication rule, extremely important. Now, conditional probability means, as the name suggests, there is a condition attached. The probabilities assigned to various events depend on what is known about the experiment when assignment is made. The moment you have some extra information in a certain event, in certain experiment, there is some extra information poured in, the probabilities would change. So when we say probability A, this is unconditional. This is the initial probability of A, when we do not have any extra information. But suddenly imagine that there is an information you're bombarded with that event B has occurred. Now I would want to revise this probability and I would want to know what happens to A given that B has already happened. So, for example, A is the event, an individual having a particular disease in the presence of certain symptoms. If a blood test is performed on the individual and the result is negative, now there is an extra information that blood test has been performed and the result is negative. You have a negative blood test. So now what will be the probability? The probability having the disease will change. The probability should actually logically decrease because the test is saying that you are not sick. This is, my friends, the conditional probability. Probability A, condition or given, condition to or given B. Through examples, I came down, through examples, I worked it out with you to figure out the formula for conditional probability. The conditional probability formula, probability A condition to B is probability A intersection B upon probability B. So basically what happens in conditional probability is, you're saying that I want to know the probability that A occurs given B has already occurred. Now that means my sample space has decreased. My sample space has decreased or it has changed. It has changed to B because B has occurred. So your sample space becomes B and your favorable cases. Your favorable case is A, right? But it's A when B has occurred. So that is probability of the intersection. That is why you have intersection here. Herein I took the help of an example. Complex components are assembled in a plant that uses two different assembly lines, A and A complement. Line A uses older equipment than A dash. So it is slower. On a given day, suppose line A assembled 8 components, out of which 2 have been identified as defective. Now, defective I've taken as B, and 6 are non-defective as B complement. Whereas for A complement, 1 defective and 9 non-defective. So the data that we have is, you have line A and A complement and you have defective and non-defective. So there are 2 defective in A and 6 non-defective, 1 defective in A dash and 9 non-defective. Unaware of this information, the sales manager selects 1 out of 18 components for demonstration. So probability line A component is selected should be equal to what? Now probability line A component is selected is just 8 by 18 because there are 8 components in A. Okay. This person doesn't yet know what is, how many are defective, non-defective. Now this additional information goes in. If the chosen is defective, now the a component that has been chosen is from A. If it is defective, then B has occurred basically. So suppose we find out probability A condition to B. That means what will be the probability out of the defectives? Out of the defectives, total how many defectives? 3 defectives. And how many are in A? 2. So the probability that you have a defective from A is 2 by 3. Okay. This 2 by 3 is actually same as saying 2 by 18 upon 3 by 18. This 2 by 18 is nothing but the probability of the intersection of A and B, that is defective and A from A, upon probability of defective, that is B. So that is how your conditional probability is basically probability of the intersection upon probability of the condition. Once you know what conditional probability is, there is a very important part that comes out of it. And that is the multiplication rule. So what is multiplication rule? Multiplication rule basically finds the probability of the intersection from conditional probability. So in case the events are such that probability A condition to B is equal to probability A intersection B upon probability B, then from here I can actually find out what is the probability of A and B, that is the intersection. I can just take this here, or I can multiply both the sides by probability B, given probability B is positive, given that B occurs. Okay, this is what is multiplication rule. Now the good part is, or the most interesting part which leads us to Bayes' theorem, is that this intersection could be found from either of the conditionals. Either of the conditional, as in you can have conditional probability of A condition to B or B condition to A. In both the scenarios, see the form, if you just go by formula wise, your numerator is probability A intersection B. In this case, the denominator is probability B. In this case, it is numerator is the same, but denominator is this, right? So what you can do is you can find one conditional from the other conditional. You can find one conditional probability using the other conditional probability. So what we can do is, see, from here your conditional probability, from this conditional probability, probability A intersection B is probability B condition to A into probability A. And from this one, it is probability A condition to B into probability B. Okay, so Bayes' theorem makes use of this multiplication rule, and in a certain scenario, suppose you are given probability A condition to B has been provided to you, you will be able to find out probability B condition to A as probability A condition to B multiplied by probability B upon probability A, because this is the intersection. Now, what is that scenario where you use it? What exactly is Bayes' theorem is something that I did work with you guys in further. Let's go through this example once again. A chain of video stores sells 3 different brands of DVD players. Of its DVD players, 50% are brand 1, least expensive, 30% are brand 2 and 20% are brand 3. Each manufacturer offer 1-year warranty on parts and labor. It is known that 25% of brand 1's DVD players require warranty repair work, whereas the corresponding percentages for brands 2 and 3 are 20% and 10% respectively. The first question that I had asked you is, what is the probability that a randomly selected purchaser has bought a brand 1 DVD player that will need repair while under warranty? So what do we need here is that, suppose AI is the event where brand I is purchased, that is of concern, and we have percentages, 50% for brand 1, then 30%, 20%. So probability A 1.5, A 2.3, A 3.2. Then let's have two events, B and B complement. B is the one where the DVD needs repair. B complement does not need repair. So in the first question that I had just asked you, that I just narrated, what do we require? We require brand 1 and needs repair, right? And what has been provided to us is that we have been provided the probabilities or regarding needs repair. Given its brand 1, it's 25% chance. Needs repair given its brand 2, it's 20%. Needs repair given its brand 3, it's 10%. So what we have to find out in the question is that what is the probability that a brand 1 brand 1 what is the probability that brand 1 DVD player needs repair? So I need B and A1. That means B intersection A1, which is something that you can get from the multiplication rule because you have the conditional probability 25% into 50, so that makes it 12.5% or 0.125. Then in the second question, what is the probability that a randomly selected purchaser has a DVD player that will need repair while under warranty? Now the DVD player, this time it's not specified which DVD, which brand. So that means I need to take care of all the three brands. What is the probability that it will need repair? Now, repair could be needed by the one which is brand 1, brand 2, brand 3. So, therefore, I will have to take care of all the three cases. So, therefore, I need the probability B, and probability B will be probability B intersection A1 plus intersection A2 plus intersection A3. So, that means multiplication rule with A1, with A2, with A3, and will give you the total of 20.5% or 0.205. The whole idea is that this demands the total probability. So B could have been achieved by A1, A2, A3. So there is a notion of total probability. And whenever there is a notion of total probability, seeps in Bayes' theorem in case you are asked for conditional probability. For example, the third part here, if a customer returns to the store with a DVD player that needs warranty repair work, what is the probability that it is a brand 1 DVD player, a brand 2 DVD player, a brand 3 DVD player? So that means what are we asked? We are asked probability that it's a brand 1, say, given it needs repair. So that would be probability A1 intersection B upon probability B. A1 intersection B I have already figured out. Probability B was the total probability I have already figured out. Hence, it's very easy to find these probabilities. 0.125 upon 0.205. So 0.61. Similarly, you can find A2 intersection B with the product rule. Similarly for A3. Okay. The whole idea is that this probability that we have just figured out in part C. This is what is Bayes' theorem. Bayes' theorem is nothing but conditional probability under the scenario of total probability because the your sample space has been divided like that. So in Bayes' theorem, there are 2-3 important things that you should keep in mind. What are mutually exclusive events? The events that have nothing in common. What are exhaustive events? Exhaustive events are when you unite all the events, you get the entire sample space. Those are mutually exhaustive events. Now, the law of total probability. The law of total probability says let A1, A2 till AK be mutually exclusive and exhaustive events. Then for any other event B, probability B is equal to probability B given probability A multiplied by probability A plus probability B given A2 into probability A2, so on and so forth till AK. Okay, that's what is total probability. I've done it right away with you, with an example, but this is what it formally means. I have even done the proof of that in the video. Please go back and see. And there comes formally, let's define Bayes' theorem. Let A1, A2 till AK be a collection of K mutually exclusive and exhaustive events with their prior probabilities, probability AI. Then for other event B for which probability B is strictly greater than 0, the posterior probability of AJ given that B has occurred is probability AJ given B. Now, B, since it could be achieved through A1, A2, so on and so forth, so therefore it will be probability B given AJ into probability AJ upon the sum of all such probabilities, like what we did in our example. So this is what I wanted to discuss in this lecture. What we have done is we have precisely quoted what all we have studied till Bayes' theorem in this lecture, and coming up in the next lecture will be a quick revision of the discrete random variables that we have worked on. Thank you very much. I hope this will be very helpful to you guys in revising probability. Thank you.